5.2, 5.1 and 5.2 have a similar strand where it's just exponential functions. This one is on applications of exponential functions, both growth and decay. Okay, so we're going to look at what exactly we can do with these. Okay, so let's look at this context. There are 500 bacteria in a dish. The amount doubles every 3 hours. Write a function that models this.
Yeah. I'm gonna get out.
Okay. So let's say that our amount in terms of time is going to be 500, and it's doubling every 3 hours. So if it was 1 hour, or 2 hours, or 3 hours, we would take that amount and break it into 3, because it takes 3 hours to make one double. Carbon-14 decays by half every 5,730 years. There is an initial amount of carbon, approximately 10 grams, it looks like, and 1.63 grams remain. How old is the sample? So you might see 14 and think that that has something to do with the amount, but it doesn't. It's just, oh, my calculator's dead, so we're just going to do this one by hand. So our amount in terms of time is going to be the initial amount times half raised to the number of years, and it takes 5,730 to make one cycle. So we have to do that. So our current amount is 1.63. Our A sub 0, our current amount, our initial amount was 10. And we had 1/2 raised to the T5730. So divide out our 10. Half to the T5730, and then since my calculator is dead, I'm going to allow you to finish this one on your own, but T, when you solve for T, you're going to have to access this term here, which means we're going to have to be doing a logarithmic power. One more here. So this is the compound interest formula. I'm not sure if it shows up on your formula sheet, but we can look over it in class tomorrow, and if not, see if there's something we can do to help us to memorize this formula, because I am seeing this on DP tests. The amount in terms of time is the principal times 1 plus r over n to the nt, where p is the principal, r is the interest rate as a decimal, n is the number of compounds, and t is the number of years. So 5,000 is invested at 3.25 for 5 years, compounded semi-annually. So I'm going to set it up and allow you to work it out. So $5,000 is our principal. 1 plus 0.0325 over n, semi-annually, the number of times it's going to compound per year is twice. And then 2 for n. And then t, the number of years, is 5. So I would work that out to come out with the amount after 5 years. So that would be the solution to this part of the table right here. What I would like you to do is fill this table all the way out and then compare the output based on n. Which is best and why? Is that what you expected? Is it not what you expected? Does it seem like it would be a better idea to have it compounding once, twice, 3, 4, 12, 365? Or is there sort of a sweet spot somewhere in there that's going to be the best option for you? And then here's sort of a pre-practice, a think about it for tomorrow. If I were to invest $350 at 2.25% and it compounds monthly, so that would be that 12, how long would it actually take for this to be worth $400? So at 2.25%, how long does it take to earn $50 on a $350 investment? So that would probably, I don't want to give any hints away, but maybe use your formula and see if you can solve it just by plugging and chugging, or do you actually have to solve an equation? So we will see you tomorrow in class.